So one of the things we need to review in order to solve ladder problems is the order of operations. The acronym for the order of operations is "Please excuse my dear Aunt Sally." Please excuse my dear Aunt Sally. Anything that's in parentheses, anything that's any exponents, and we do have some in the example problem we're going to give, then multiplication, then division, then addition, and then subtraction. That's always the order you do all of your math in. We have a problem, an example problem, where you are given a venturi, right? And a venturi, I feel like I could have drawn that better, has an area, cross-sectional area, right? From here to here on the inlet is the same as what's on the outlet. But here in the middle is narrower. So, because the mass flow rate going in is the same as the mass flow rate going out, something has to change in here for that mass flow rate to be the same. And what happens is, as the area goes down, the velocity of the fluid goes up. And as the velocity goes up, the pressure goes down. So imagine a bunch of people, all these people backed up right here, trying to fit through a narrower doorway, right? In order to get through here and continue at the same speed that they were going here, they have to go through here faster. And actually, because there's fewer people around them, there's a lot less shoulder to shoulder pressure as they're moving through. That might be a silly way to think of that, but it helps people. So if the area goes down, the cross-sectional area, right, the width of the pipe goes down, the velocity goes up, they're moving through there faster, and with less pressure, the pressure drops. And that's what this problem is trying to solve, is it's trying to say, hey, what is this pressure drop? I won't go through the conversion from the general energy equation to the equation to use, but all you're doing is eliminating the things that you're not using, right? No change in elevation, so you can get rid of anything that has to do the G times Z, the change in height over G sub C. You can get rid of that. You can get rid of the internal energy. You can get rid of the work. So all we're dealing with here is the difference in pressures and the difference in velocities. So pressure 2 is equal to pressure 1 plus. Now, I want to stress this right now. This is not part of the ladder equation. This is the pressure, the initial pressure here, the what do they give us, 120 psig? Here, that's all that is. Now to that, we're going to add whatever the pressure drop is. And that pressure drop, so this here, the change in velocity, the V1 squared minus V2 squared, and I saw several of you that didn't do the squared velocity, over 2 specific volume, the weird V, G sub C. Because if you remember, the potential energy, the kinetic energy is equal to 1/2 mv squared. So that's what this is adapting. We're adapting this from the general energy equation. We've factored the mass out. So all we're worried about now is the change in velocities. This is what we're going to set up on our ladder problem. And we know in the problem that you're given in your PowerPoint that it's 20 feet per second squared. Or sorry, 20 feet per second. But this whole thing is squared. minus 45 feet per second. And this whole thing is squared. So what that means is we're going to end up with 20 squared feet squared second squared. This is important for solving this. Some of you had a hard time with the units, so I want to get these quick concepts out of the way, these problem areas with this, so that you know what you're seeing in the equation when we set it up as a ladder problem. All right. So this v1 squared, this velocity 1, is this velocity, 20 feet per second, squared, which means 20 squared feet squared per second squared. All right? And it's the same with the 45. 45 squared feet squared second squared. Because all we're doing is we're moving that squared into each term in the equations. All right, so it's effectively a parenthetical. Remember, please excuse, before we do the squaring, we got to solve the parenthetical. So 20 feet per second squared. All right. All right, so before we set up our ladder problem, pardon my jumping into that a little early there, let's ignore that for a second. Let's solve just this part, right? So we'll do our 20 squared feet squared per second squared minus 45 squared feet squared per second squared. These equations are often done best by breaking it up into smaller chunks. All right, so let me get my handy dandy calculator here. 20 times 20, 400. All right, so 400 feet squared per second squared minus 45 times 45, 2025. 25 feet squared per second squared. So 400 minus 2025. Negative 1625 feet squared per second squared. All right, so now we can set up our ladder problem. I've done that initial solve for the difference, and the reason that we're doing that first is intuitively you would see that this is actually should be in parentheses. This v1 squared minus v2 squared. This should be in parentheses, which means it needs to be solved first, which is why we're doing that. Because we can't do the math right in the right order without solving this parenthetical first. Then we get our answer, 1625 feet squared per second squared, and it's a minus. Now let's just carry out our ladder problem. All right, I'm just going to extend that line there, and this is all that goes on the top. The velocities, we've already solved that. Now we just figure out what goes on the bottom. 2 goes on the bottom. See that? The specific volume, which is 0.016049. Well, I'm just going to use what the PowerPoint was off by 1/100,000th. Anyway, 50 feet cubed, and because it's cubic feet per pound mass, instead of writing the per pound mass down here, we actually, this is on the bottom, and so the pound mass goes on the top. How do I explain that better? When something like pounds force per inch squared, right, is written this way, but this number, whatever this number is actually on the bottom of the equation, then it just flips this. So it would be, it's like this. Something up here divided by x pounds force per inches squared is the same as something up here divided by x pounds force times inches squared. So that's all we're doing here is when you're on the upside down, when you're on the upside down, everything's flipped. So the things that are normally on the bottom of the normally on the bottom end up on the top for the upside down. All right. Now, G sub C, which is 32.2 foot-pounds mass per pound force second squared. Okay? So this is my ladder problem without any conversions. Let's see what I have that cancels out. I have seconds squared cancel out. Pound mass cancels out. I have 1, 2, 3, 4. So there's cubic feet here and a foot here, so that's 4 feet, right? It's this foot times cubic foot is the same as writing foot, 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 4 of them, which is also the same as foot squared, right? However you want to do that. So there's 2 of them in the top, which take away 2 of them in the bottom. So I'm going to cancel out this one here, and I'm going to make this a squared. So now we're left with pounds force per square foot. But what we need is inches squared. So we're going to do the 1 foot squared is 144 inches squared. All right. Now, the only numbers I have in the top is minus 116.25, and then I have all this in the bottom. So trying to figure out how to put this into a calculator, yeah, it's a little tough sometimes. Let's just solve it a piece at a time. I already know what's on the top of my equation. It's minus 1625. And I know that the units on the top are pounds force. Now I'm just going to do the math for the bottom. So you do the top separately from the bottom. 2 times 0.016050 times 32.2 times 144 equals over 148.84. And my units on the bottom are inches squared. Now that I have this, now I don't have to worry about any calculator functions that are complicated. I just take 1625 negative divided by 148.84 equals minus 10.92 pounds force per inch squared. And because this is a negative, if we go all the way back up here to the P1, right, this is 120 plus whatever I came up with, which is plus negative 10.9, which means the same as we're taking away, that pressure drop is 10.9 pounds. So our pressure 2 is 10.9 pounds less than our initial pressure of 120.